to account for the coefficient, because like if I have 2, that's going to be, if I have 2 of this, it's going to not be consumed. It's going to be consumed twice as fast, I think. Yeah, I think. And then I'm going to put a negative sign. Okay. To show that it's going down, right? And then same thing with B. B is also reactant, so it's negative 1 over B, d B dt. I could also just say rate of B instead of this. This is rate of A, and this is rate of B, and then rate of C is 1 over C dC over dt. This is rate of C. Have you guys seen this before? So basically, this is like, and then this is, remember, this one's positive because it's a product, right? So he might ask you a question like, in the reaction, like in the generic reaction, 2A plus B yields 2C plus 2D plus E, right? What is the average rate of the reaction, right? And it's also given that the concentration of A went from 10 molarity to 6 molarity. This is concentration of A. And then T equals 200 seconds. So it went from 10 to 6 in 200 seconds. Does that make sense? So if I calculate, so again, how much did this went from final minus initial, A went down by like 4 molarity, right? Divide that by seconds, you get a rate, right? What is that rate? It's the rate of A, right? And it's asking for the average rate, which is the overall rate of the reaction. Does that make sense? So you would write it as, so again, you can write B and stuff down, but you only care about this part because it only gives us information on that. So if we know that we're trying to find the overall rate, and we have negative A dA dt, we're going to eventually use this equation, right? But before we do that, we need to calculate the rate of A. So this is going to be final minus initial. Remember, any change, D concentration is like final minus initial. Like, remember, average, right? So this went from 6 molarity, final minus initial 10 molarity, over 200 seconds. This is going to be negative 4 molarity over 200 seconds, which is 1 over 50, which is 0.02 molarities per second, negative. Does that make sense? So then now I'm just going to bring this up here so you guys can see. So I'm looking for the rate, and I know that the rate is negative 1 over the coefficient of A, which is, what is it? 2. Negative 1/2. And then the rate of A, which is negative 0.02 molarities per second. So then the overall rate of the reaction, the average rate of the reaction is 0.01 molarities per second. Does that make sense?
So in this case, the overall one is just A because that's all it gives you.
Say it again?
Like the overall rate is just for A because it only gives you A? Like,
yeah, it only gives you A in this problem, right? So let's say I ask you the overall rate of the reaction is 0.01 molarities per second. I ask you what is the rate of A. Just to put this into perspective, you need 2 of A per 1 of B, right? So if I have like let's say I'm like making a toy, I don't know, I'm in a a factory, right? And I have like one toy requires 2 parts of A and 1 part of B, right? And so like I grab 2 from here and 1 from here and put it together and move on, right? So and let's say I started with the same amount, right? Which one's going to finish faster?
B.
A. I'm grabbing 2 at a time versus B. I'm just grabbing 1, right? So the A is being depleted twice as fast as B, right? Because I'm grabbing 2 at a time. Does that make sense? So, for example, if and then the rate is going at a certain rate, right? So if the rate is 0.01, that's the average rate. How fast is A being depleted? Twice as fast as the average rate, because I'm using 2 for just 1. Does that make sense?
So what if it gave you like info for A and B? Like, would you calculate?
If it gave you for info for A and B, 1 you could use either one. 2 it should all equal to each other.
Oh.
So like let's say B went from 10 to 9. Yeah, 10 to 9 in like 10 to 9 in 100 seconds. Okay, so it went from 10 to 9. So 9 is the final. Initial is 10 over 100. That should equal negative 0.01 layers per second, and this is the rate of B, and then 1 over the coefficient. Coefficient B is 1, so it'll be they'll give you a number like that. It should all equal. Yeah. Okay. Does that make sense? Okay, and then let's give you one more. Okay, does that make sense? I feel like you guys can figure that one out. And then, okay, let me go over one more thing. Going back to the charts. So going back to the charts, so again, there's this, and then there's this. Let's drop 3. So there's 3 types of graphs you can have like this. You can have it like this, and you can have it equal. Over here, is this positive or negative delta G?
Negative.
Negative delta G. This one?
Positive.
What about the last one? If I start at 5 and I end at 5.
0.
Delta G equals 0. This is called exergonic. It's like the proper name for it. This is called endergonic. Is it spontaneous or non-spontaneous? Spontaneous. This is non-spontaneous. And then this is at equilibrium.
Right.
Is K greater than or less than 1 here? Greater than 1. This is less than 1. This is K is equal to 1. Which one's more stable? Products or reactants here? Products are more stable is lower, right? The products more stable. Reactants here are more stable. And then products and reactants are equally stable. Know those trends. It might give you graphs. Which one is spontaneous? Which one has the lowest activation energy? For this one, which one would have the lowest activation energy. First one, it's like this big versus that's this big, and then this one's like a little. Like it'll be more distinct on the test, but like that's the idea. He might ask you like those questions. Okay. One more thing. One last thing. Okay. So as he can I erase this? So, have you guys seen this equation? K equals A E negative E A over R T. Have you guys seen that? No? Really? Do I even bother?
Is that big K or small K?
Say again?
Is that big K or small K?
The small K. He's never given you this. So if I doesn't give you this here, I don't want to like talk about it. Are you guys? If you can double check, that'd be nice. But this was at least on my quiz. Has he given you this one?
Maybe he'll show it today.
Maybe he'll show it today. I'll just go over it just in case. So you should know these two. I think he gives it to you, but even if he doesn't, okay. There's these two equations, right? This one is just saying, so EA is the activation energy, right? That's usually like it's in joules per mole, okay? Or just joules, like like joules per mole or joules. Like it will most likely be in joules if you have that, okay? So activation energy would be like 10 joules. You plug that in there. Does that make sense? Okay. So activation energy will be like a unit. This is R 8.314, same as what you're used to. What you're calculating with this is the rate constant, and this is the temperature for that rate constant, and then you're calculating what the rate constant would be due to a change in temperature, right? Like all the time, like basically the higher you raise the temperature, the faster the rates will be, okay? And the higher the rate constant value, right? So if I change this, if this is like at 300 Kelvin, I'll have some rate constant, and I can figure out how much it would be at 500 Kelvin. I have some rate constant, but I have to be given the activation energy. Or you can be given both of these, and it says what is the activation energy. Does that make sense? So this one is more plug and chug, right? Does that make sense? Yeah. And then this one is kind of like plug and chug too, except A is like some just constant, like he'll give it to you, A equals 1 or A equals this. Does that make sense? He'll give you what A equals, okay? And one thing I saw he did on a quiz, like this will make more sense when, basically is like, this will make more sense when he goes over in lecture, hopefully. But this is little k, and then activation energy, temperature R, and then some constant, okay? Now what it's basically, he'll give you like, this is the value of A. What is the rate constant if the activation energy is this at this temperature? Does that make sense? And it's plug and chug there. Now one thing I've seen him do before is he'll give you a graph, and he'll say like, what's the activation energy? And it's like a line graph, and you're like, how do you do that? But you have to look at the axes, right? So let me show you something. Like I'm gonna just kind of make this a little nicer, right? So what if I natural log both sides? Okay, if I did that, I can separate these two. Okay, I can separate those two, right? I'm gonna switch these two real fast. So I'm gonna write up natural log K equals natural log E